Hello out there, and here we are with the week 3 video number 3, and it's only Wednesday, so I'm getting a bit earlier in the week getting these things out. We should be fully caught up, I think, by next week to where I want us to be. So for this video and the next video, I'm going to be going to go over basic syntax in the 386 assembly language, particularly the NASM version that we are using. And but to understand the syntax, you have to know a little bit about what's going on inside the computer. So we're going to take a simplified view of the architecture of a 386 machine. And I do kind of have a caveat on this diagram I'm providing you, and I just want you to make sure that you keep in mind that I'm not really showing you everything that's going on. I'm showing you the things you need to know to understand the assembly language that we are going to be working with. I may get deeper into this at some point and show you more of what's going on behind the scenes here, but just so you're aware, this over here, this side, I can't really highlight it properly. Let's see if I do that. Well, if I just hold the cursor, so you can kind of see the area I'm highlighting. This is representing the computer's memory, the RAM. However, it is not really the entire computer's memory. It's a virtual memory, and this is not a virtual memory that is the same thing as your virtual machine. Your virtual machine is the simulation of an entire computer. Now let's pretend that that virtual machine is a real machine. Then still that real machine has virtual memory. Okay, so and even your Windows machine is doing something similar to Linux, but it does some of its own things. So not everything is going to be exactly the same, but it's going to be along the same lines. Windows is still going to be having reserved sections, and it's going to have a heap and a stack, and it's going to have a virtual memory layout that is at least somewhat similar to what we have here. So your real Windows machine, if that's what you're working on, has something like this as well. So there's layers of virtual on top of virtual on top of virtual in computing nowadays. It's just something you kind of have to get used to. So we are looking at the virtual memory that a single running program sees. So the single running program thinks it has access to a complete machine, including the virtual memory that I'm showing you here. And this is 4 gigabytes of virtual memory. Now that amount of memory may not physically exist, so your running programs may not ever actually get to use a total of 4 gigabytes, but at least they in effect see what we call an address space that is 4 gigabytes. So if you look at the addresses I've put on this, now let me zoom in a bit and center it. Yeah, that was a little too much. But if you look at the addresses that I've put on the side here, you'll notice that they start at 00000000. These are hexadecimal. That's what the 0x in front of the number means. And they go up to 0xFFFFFFF. So that is 4 bytes. So the maximum value in 4 unsigned bytes, and I think I posed this as a question to you the other day, but let me just write it down here so you can see what I'm saying. Maximum value of 4-byte unsigned int or 32-bit. Actually, let me say 4-byte or 32-bit. What is that? Well, that's 0xFFFFFFFF, right? That's 4 bytes with all ones, okay? So if we remember, each F in hexadecimal is 4 1 bits, okay? So this is 32 ones, okay? And the value of that in decimal, that is 2 to the power of 32 minus 1. And if you multiply that out, compute that, that equals approximately 4 billion. Okay? In other words, we're talking about 4 gigabytes. Okay? That's your standard memory space for a 386 architecture. Again, you have all of these addresses available in a 32-bit address. Even if physically you don't have that much memory, that is the range of addresses that you have. If you have less memory, then there's going to be some juggling done by the operating system to make sure that you only use those parts of memory that are available. And there may even be situations where you have more physical memory, but a single running program only gets to use up to 4 gigabytes of it. And I know I keep switching between giga and giga. You just have to roll with it. I can never decide which one I prefer. So at any rate, that's the memory, that's the virtual memory that every process has. And what that allows is each process can then be kind of arranged within that virtual memory without worrying about any other process using any of that space. All of that is the fact that many different programs are all simultaneously running on the same computer is handled by the operating system, and all that juggling of the physical memory and which process has access to what is handled behind the scenes. Okay, but for our purposes, we get to pretend that a single running process has access to the entire machine. So let me go ahead and write that down too, just so you get what I'm saying. We get to pretend that a single running process in what is called protected mode on an i386, we get to pretend that that process has access to the entire machine. A full 4 GB of main memory, all the registers, which we're going to talk about what those are in a moment, etc. Okay? So each process gets to run in its own sort of virtual world where it thinks it has absolute control over a machine, but it doesn't really. A process has to run in real mode to truly have control over the real machine. So I'm going to go ahead and make a note of that. A process must run in real mode to have true access to the entire physical machine. Okay, usually that is kernel processes of the operating system, and only those get to do that for security reasons and so forth. You don't want just any program that's running to have complete control of the machine. So that's why we're looking at a simplified diagram here of just what a processor thinks it's working, of the basically kind of the machine that a process thinks it's working on. And aside from the fact that this is virtual memory, there's a whole question of caching, which we're not looking at here. So again, a number of simplifications here, but these are the things that you need to understand how your assembly language programs work. All right, so aside from main memory, the other important thing to look at are what we call registers over here. Now, what are registers? Registers are very small memory locations that are in the CPU itself. So I don't know, some of you may have built your own computer. You know, you get your DRAM, you insert your DRAM. The DRAM gives you real main memory, okay? So, but this virtual memory basically corresponds to access to the DRAM. And those are on completely separate chips from the CPU. The CPU has registers. It also has cache, which is much larger, much smaller than main memory, but much larger than the few bytes that you get in registers. But we're not worried about cache. We're just worried about registers. Registers are the tiniest, fastest memory in a computer. Okay? Basically, what you can say is that the smaller the memory, the faster. So registers just give you a few bytes of memory. If you look at what we're working with here, I'm showing you most of the registers that a 386 CPU will have. There are a few that are not listed here, but they're ones we're not really going to worry about. We may eventually look at them somewhere down the road, but these are the important ones for now. And you notice I've illustrated the number of bits in each of these registers. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 4-byte registers. So a total of 40 bytes of register memory. That is all the CPU has to work with to do all of its basic operations. Whenever you're running any real-world program, and you might have an array of 1,000 integers, or character arrays of hundreds and hundreds of bytes of text, or megabytes of text, or just you could have whatever. I mean, you have 4 gigabytes, 4 billion bytes possible out here in memory here. And of course, in newer architectures and 64-byte architectures, the size of memory gets even larger. You get some more registers as well, but you can see a drastic difference. We're talking about a factor of about 1 billion between how much memory you have in registers and how much memory you have in main memory. But accessing main memory and getting data from it into the CPU so the CPU can do mathematical operations or whatever else it needs to do, and then transfer those results back to main memory, that takes forever compared to just doing something with what's in registers. So registers are where things happen fastest. Programs get slowed down a lot just from the fact that a lot of the time they have to transfer stuff from main memory into registers and from registers back to main memory. And they have to do that a lot. But if you can write a program so it avoids making unnecessary transfers to and from memory, you make a much faster program. This is one of the reasons why assembly language even is still important. That to write certain pieces of system software, like software drivers for hardware and so forth, you want those things to be absolutely blindingly fast as possible. And that is one reason why some people still actively do programming in assembly language. Often you start with C programming, then you take what the C programming compiler produces, and then you look at the assembly language that produces and tweak it to go even faster. And one of the main techniques of making your program go faster is by finding unnecessary transfers to and from main memory and eliminating them, so that you keep things in registers until everything you need to do with that piece of information is done. Then you send the result back to memory, and avoid a lot of additional back and forth that often happens from just, say, a compiled C program. All right, so what are registers? Registers are basically 1, 2, or 4 byte locations that can be each have a name and can be used to store either 1, 2, or 4 bytes. In 386, your registers are really 32-bit registers. All the important ones are, at least the ones that we're looking at now. There are some other registers that are 16-bit. So we have general purpose registers, EAX, EBX, ECX, EDX, ESI, and EDI. Then we have some special purpose registers, ESP, EBP, E-flags, and IP. Now I've put the names of these kind of small. Even if you're looking at this in the notes, you might want to zoom in the view in order to see more clearly here. But so we have EAX, EBX, ECX, EDX, ESI, EDI. Those are general purpose registers. You can do most operations mix and matching these registers for any of them. Some operations may only work with some registers. But then when you start getting to ESP, EBP, eFlags, and IP, you either don't want to touch these directly or you want to be very careful what you do with these. So generally speaking, you don't want to do anything with ESP, EBP, eFlags, or IP directly. And let me go ahead and talk about what those are first, just because they're a little bit, well, I can't really talk about ESP yet or EBP yet. We'll get into those later. But let me talk about IP and eFlags. So IP first, because it's the easiest to understand. The IP register is what we call the instruction pointer. And that stores the 32-bit address of the next instruction that the CPU is going to execute. Okay? So, so before, when we were looking at opcodes in the hex editor, let me come over here. So if we look at our first ASM program, and remember that we found some instructions. Like here's the very first instruction in the program, right? And so, and that ends up being at the address. See if I can find a copy of it here. Actually, there we go. And this is the address where that first instruction occurs. Of course, it's a little endian, so you got to turn it around. But that is the address, okay? Now, if we look at my diagram now, I actually am pretending in my diagram that we've done the first instruction, which is 5 bytes long, and we've done the second instruction, which is another 5 bytes long, right to there. And we are ready to do the next instruction, which starts on that byte, and it's also 5 bytes long. But that's the byte we want right there. If you look down at the bottom, offset OX8A. Or we can just think in terms of that's 10 bytes after the initial address. And we did that conversion of what that address is. You have to do the little endian. But if we come over to my diagram, I have it in there. So, whoops, brought up the wrong one. So let's look here at what I have in the memory diagram for a moment. I have the text segment. Basically, this is how memory gets laid out when your program gets loaded. There's a little reserved section that the operating system messes with. Don't worry about what happens there. Then your .text segment of your program starts at typically this address. This can be different under some circumstances, different operating systems and so forth, or even different variations of Linux. So this number is not written in stone, but if you'll remember what we looked at last time with the readelf command, and we see the address let's see, we see the address of start, we see the address of the text section. That should be where text starts. No, text starts. That's not the address of text precisely. This is the address of text. Okay, so that's where we get that from. And now I need to go back to this diagram. So that's what we have here is the beginning of our .txt segment. And so that is also the address of the first instruction in at least in our example first assembly program. We could make the starting instruction be somewhere different. We could force it to be somewhere different. But typically your .text, the first thing in your .text segment is the first instruction. And so this will be the address of the first instruction. So now if we look at my IP register, what do I have in here? So maybe pause and test yourself. Can you convert this binary into hexadecimal, both decimal and hexadecimal? Hexadecimal is actually easier. You'll see each 4 bits of binary converts to a hexadecimal. So this is O, this is 8, that's 0, this is 4, that's 8, 0, 8, and this is 8 plus 0 plus 2 plus 0, so this is a 10, so that's an A in hexadecimal. So we're actually at position if the instruction pointer had this number in it, that would mean we were ready to execute the 3rd instruction in our example assembly program. So we would be ready to execute this instruction right here, because we've already done the first instruction, that's 5 bytes, second instruction, another 5 bytes. So we're 10 bytes after the first instruction, so if you just add 10 to that initial address of the start position of the entry point, then that is where we would be. So actually I'm going to throw in a little text box here. Why not? And say 0x080480. Now we have to add 10 to this. 10 in hex is an A. You just add that A to the first digit. 0 plus A is A. So there we go. Oops. 8A. There we go. And that is right there. Actually, I think I'll add just a little bit more context here. So next instruction. Okay, so again, using the instruction pointer says where the next instruction is. Now, you almost never would have a reason to directly change the instruction pointer. It just automatically adjusts itself. So when an instruction occurs, such as what we have, those 5-byte instructions over here, so when it does this instruction, it automatically knows that instruction took 5 bytes, and so it adds 5 to the instruction pointer so that it's ready to do the next instruction when the last instruction is finished. And then it adds 5 bytes to get the next instruction. Not all instructions take exactly 5 bytes. You can have instructions that are just 1 byte. You can have instructions probably up to 10 bytes long are possible. Maybe even bigger. I'd have to think about it. But definitely not all the same size. But whatever instruction it has, the CPU knows how big that instruction is and knows what to increment the instruction pointer to. There are also jump instructions that move execution to a different place in the program instead of just doing the next instruction in sequence. That's what allows you to do branching, to do if-thens, and allows you to do loops and so forth. So so those instructions that do jumps modify the instruction pointer, but you never have to directly write a command that directly modifies the instruction pointer. It just happens automatically. Okay, so that's the instruction pointer. Now there's the flags register. The flags register is another very special register. I've shown all zeros here, but what is in here really just depends on what the most recent instruction was, or sometimes it can be affected by a few instructions previously, but most of what we're interested in is described down here. Let me zoom out a bit. So I've got this chart detailing the E-flags register, and I've highlighted the 5 flags that we are likely to care about in this class. I don't think we're going to do anything where we need to worry about the other flags, okay? But here we have the overflow flag, sign flag, zero flag, parity flag, and carry flag. The zero flag and sign flag are probably the 2 most commonly used ones. And shortly after that, the overflow and carry flags. and finally the parity flag. The 0 flag basically gets set to 1 if you do a computation whose result is 0, like you subtract one number from another number and get 0. Or if you add two numbers together and get 0. Add a positive to its negative, get a 0, right? Then the 0 flag gets set. It will also get set if you do a comparison operation and the comparison was equal. That's because the way the CPU really does comparisons is by subtracting. And so if you subtract one number from another number, then 0 means the numbers were equal. All right, so and the result of the subtraction is thrown away. Okay, so that's something to keep in mind as you start learning the actual arithmetic commands and so forth in the assembly language. When you do a compare, you compare two things to each other, but the result that's really done by doing a subtraction, but the result of that subtraction doesn't go anywhere. If you want to, but you can, if you need the result of the subtraction, you can do the subtraction and then still use the 0 flag to determine if the one thing that you subtracted from the other thing, if they were equal. So the 0 flag is fairly important. And I think I'll add to this little box here. That flags are most often used for what are called conditional jumps. Examples are things like JEQ, let's see, JNE, JLE, that sort of thing. So let me take off the bold. That's jump if less than, I mean, not jump if less than. That's my last one there is. Jump if equal. Jump if not equal. Jump. Jump if less than or equal, and so forth. So these jump commands, and we'll be looking at these in more detail later on. I just want you to give it, you're just getting a feel for things and learning your way around right now. So the jump instructions, most of them, there is an unconditional jump that doesn't look at the flags, but each of these looks at the appropriate flag register to determine its condition. So JEQ would look at the 0 flag, and it wants it to be 0. JNE wants the 0 flag to be a 1. JLE wants the sign flag. I think it wants this, let's see, it's easy to get this backwards, but I think it wants the sign flag to be a 1. Because JLE is going to do a subtraction. Well, that's not going to do the subtraction, but if you compare two numbers together, it does a subtraction. If the second number is smaller, then that means the first number is less than the second number, right? So JLE is looking for the sign to be 1. It's easy to get that backwards, so you just have to be careful. You can use the other one, jump if greater than, and so forth, and you can look those up. In fact, why don't I go ahead and give you a link to more info on the jump commands, because you're going to need this soon enough. I have this over here. Let's see. Yeah, this is a pretty nice web page, at least for the jump commands in assembly. And pretty well summarizes what each jump command does. And in fact, I wrote my mnemonic wrong because it's JE, not JEQ. So let's go ahead and fix that. Over here, JE, and then if we come back over here, yeah, JNE was right, but JEQ was wrong. Then let's see, we find, so here's JGE, greater than or equal to, JLE, less than or equal to, and so forth. And these also tell you what flags it wants to look at. So overflow flag, the 0 flag, the carry flag, the sign flag, and so forth. And in some cases, it depends on if one flag equals another flag. So definitely something to be aware of. Generally, you may not even need to really worry about the flags. You just have to know, if you did a comparison in the previous instruction, then you can do a jump based on the result of that comparison, and you don't have to think about the flags. But if you want to really get into the technicalities of it, you need to know what these conditional jumps do based on the flags. Conditional jumps are basically your way of doing both ifs and loops in assembly language. So let's actually put that in there. Conditional jumps are the way you do if-else in assembly. Well, that's actually if-else and loops in assembly. So you don't really have an if or a while or anything like that. You just have these jump commands, and the jump checks the flag and determines whether or not it actually makes the jump. And like, that's as much as I'm going to say about jump commands right now. We're going to get into the nitty-gritty details of that soon enough. But now you basically know what the IP register and the E-flags register are for. And you'll notice the E-flag register has 32 bits. A lot of those are not really even used for anything, and only 5 of them are really interesting to us in this class. All right, so what about these other 6 registers over here on the left? We have EAX. You've already seen these in the program, right? EAX, EBX, ECX, and EDX are each 32-bit registers. Now, one strange thing you will notice is that because of backwards compatibility with earlier versions of the x86 architecture, we actually have smaller registers that represent part of the bigger registers. So, for example, AX, BX, and so forth come from the world of 286, okay? And going back even further, you have the 8086, which only had 1-byte registers. Everything had to be done in individual bytes. So the AX register represents simply half of the EAX register. The E actually stands for Extended AX register, okay? So once they went from 16 bits to 32 bits, you got the EAX register. Previously, you had the AX register, which represents only the second half of EAX, the smaller half. And then we also have a register AH and AL, okay? And those 2 registers are each 1 byte, and they are each half of the AX register. So you have to realize, if you change the AL register, you are also changing the AX. You're changing 8 bits out of the AX register, and you are changing 8 bits out of the EAX register. If you change the AX register, you are changing 16 bits, half of the EAX register. And then we also have the same thing for EBX, ECX, and EDX, and almost the same thing for the ESI and EDI registers, except they don't, so you also have an SI and a DI register, but those don't get further split into halves. So you don't have any 1-byte versions of the ASI or EDI registers. But it is important to realize that the AX register is a part of the EAX register. You cannot change the AX register without changing EAX, and vice versa. If you change EAX register, then you've completely changed the AX, the AH, and the AL, and so forth. Now, these 6 registers are considered general purpose registers. I think I want to start putting this into notes somewhere. No, I think I'm going to add another page, slide this up here. Let's call this 386 Architecture. Alright, and we'll just start having notes here. So then I'll make this thing a subpage of that thing. Alright, so what we're talking about then is the registers here. I think I'll zoom in a bit. There we go. So, registers. So we have the general purpose registers. We already talked about the instruction pointer, the E flags, and now we have the general purpose registers. So this is EAX, EBX, ECX, EDX, and ESI and EDI. Okay. Now, although these are general purpose registers, each one is traditionally used for certain purposes, and some instructions can be used. Some instructions will only work in certain ways with certain registers, and those are details that we're going to learn more about later. But most instructions work with any of these, okay? And variants work with the half and quarter registers as well. So most instructions that you learn about, you will be able to, so for example, you learn the add instruction. You could do things like add EAX, EBX, or add ESI, EDI. Basically, any 2 registers you want to put together, ECX here, whatever. Any 2 registers you want to put together, or move EDX5. So almost any variation here of which general purpose register you want to use with these commands will work. In fact, some of the other registers we're seeing can work with some of these commands as well, but you usually don't want to. So you can use the ESP, EBP, maybe even the E flags, maybe. I have to look at that. I haven't really tried it. There's almost never a reason why you would touch either of these 2 registers directly. There are sometimes you might use ESP and EBP like additional general purpose registers, and for the most part they could be used that way, but it's dangerous, and in most kinds of real world programming situations you would not want to do that. But the general purpose registers, and let me go ahead and say C diagram here. But the general purpose registers, most of the different kinds of actions you can perform, you can mix you can mix and match the registers as long as the you use the same registers of the same size. Must use registers or operands of same size when there are two operands. Okay, so so you can't mix. You cannot do something like this. Okay, that should not work. You need to have two registers of the same size, for example. So this says add EBX to EAX. For example, this one will add ECX to ESI. Result will be in ESI. So in the syntax we're working with, generally speaking, for example, with the add commands, the destination where the result of the operation appears goes into the first operand. So here you add these two numbers together, but then the result replaces EAX. So it's like this is sort of like EAX saying EAX equals EAX plus B or EBX. Okay, similar to that kind of C programming thing, except registers are not exactly the same thing as variables, but you use registers like variables. So this is what that add command does. This is similar to saying EDX equal 5. All right, in C. Oops. EDX equal 5. So might as well complete this. So like C programming, ESI equals ESI plus ECX. Now you might ask, Scott, hey, can I do something like this? Can I do something like what is similar to C programming? EAX equals EBX plus ECX, because you can do that in C programs, right? Surely you can do that in assembly language. Well, actually, sorry, not available. So that may seem a little strange, but yeah. When you do an addition in assembly language, you're actually destroying one of your operands of that addition. One of the two numbers you're adding together, you're throwing that number away and replacing it with the sum. Okay? You're stuck with that. To do this, you need to do extra steps. You'd actually have to keep, if you wanted to preserve EBX here and add it to ECX, you need to keep a copy of whatever number you had in EBX somewhere else. Okay? So you cannot do this. Right? Let me go ahead and... Oh, it doesn't have it for me. Let me strike that out because you can't do it. Okay? But most things that you can do with any one of these registers, you can do with the others. There are some traditional uses that are applicable to each of these registers, and for some instructions those still apply. We'll probably talk about that later. I'm not going to try and get into it in this video because we're already at 45 minutes. So, but I will just note there are some traditional ways in which each of the A, B, C, D, E, S, actually I should say SI and DI registers are normally used. But we'll save further discussion of that for another time. I don't want to get into that too deeply because we've already covered a lot of ground here, and I'm going to want to wrap this video up. But let's talk about what assembly language programs do. Everything in an assembly language is basically about either doing arithmetic, some kind of arithmetic or other simple computations on stuff in registers, and or moving things from registers to memory, from memory to registers. So let's just think about that in the context of our example program, which doesn't do a whole lot, so there's not a whole lot to see here, but let's go ahead and bring that up. And you'll see that first we have a move. In fact, the only interesting instruction we have here is the move instruction. Well, the interrupt's pretty interesting, but that gets into some technicalities I don't want to talk about right now. So all we have here is 4 moves, okay? And these 4 move instructions each are just moving something from memory into EDX, okay? And I've expanded the comments here so you have a lot of information kind of describing what this does. But it's basically going to take the number that comes after the opcode for this instruction, the opcode here. It's going to take a number and move it from memory into EDX. So if we look at the diagram again now, and we zoom into memory, and this is where maybe I'll do another diagram to help clarify this. But right here in memory where this arrow is pointing, that's where that instruction is, okay? And that instruction and then 4 bytes after, so it's a total of 5 bytes. Well, the first byte is the opcode saying what the instruction is. The other 4 bytes are just the number 18, or 12 in hexadecimal. And so we're taking the 4 bytes that it would be right here in memory, where basically where my cursor is, there would be 4 bytes right here, and we're going to copy those 4 bytes into this register over here. Let me zoom out now. So EDX, so it was a move to EDX, so we'd be getting 4 bytes from memory over here and moving those bytes into the EDX register. So these bits that are zeros now would suddenly have whatever bits that the 4 bytes in memory there had, okay? And so you'll notice that our simple little program, that's all we do is move something from memory. We get another 4 bytes. Those again be right there in memory right after the instruction, and we move those. We'd have another 4 bytes that just represent the number 1. We'd be moving those from memory into the EBX register. And we have another 4 bytes representing the number 4 and moving those into the EAX register. Then we do this int command, which int stands for interrupt. And what the int command does basically depends on what's in these 4 registers that we just move stuff into. So really all we're doing here is setting things up to do this int command. And the reason for the int command is so we can do what's called a system call, in particular a syswrite, and it's going to take the information in these 4 registers. And the most important piece of information there, I guess, is this number right here, which is going to be the address of this data in memory. And then when it does the syswrite call, it's actually jumping into the kernel section of the program. So if we go back to our memory, or our diagram, that interrupt is going to ultimately have the effect, it's actually going to change the instruction pointer, because that instruction pointer is now going to be going, it's going to find the instructions for the syswrite call that are going to be somewhere here in this area reserved by the Linux kernel. That's where all the instructions for things like system calls are located and so forth. So it's going to do the instructions here for the syswrite, and then it's going to jump back to where it left off and go on with the next instruction. And so then the next instruction is just move something else from memory into another register, and move something else from memory into another register. Now, obviously, we're going to get into more interesting programs where instead of just moving things, we're going to add things. And there's other things besides just moving an immediate constant from right where the instruction is. There's pointers, and so you go to where the pointer is pointing and get what's there and move that. And there's moving things from one register to another register. And then there's, arithmetic operations and so forth as well. So there's a lot more interesting stuff to get into, but hopefully this gives you now kind of a framework to start understanding what the assembly language instructions are actually doing. And so that'll wrap it up for this video, and I'll be getting another video out hopefully by tomorrow. I want to keep cranking these out and get us caught up to where we need to be. All right, so until next video, I'm signing out.